NASA's twin Voyager probes, launched in 1977, awed the world with historic journeys to Jupiter, Saturn, Uranus, and Neptune. Both probes continue their trip into interstellar space 45 years later. Researchers, some of whom are more recent than the spacecraft, are currently using Voyager data to unravel mysteries within and beyond our solar system. In many ways, NASA's twin Voyager spacecraft have evolved into time capsules of their age. They contain around 3 million times less memory than contemporary cell phones, transmit data at a rate about 38,000 times slower than a 5G internet connection, and each has an 8-track tape recorder for data storage. Despite these limitations, the Voyagers are still at the forefront of space exploration. What are they doing right now? What will the Voyager spacecraft encounter next? Let's find out. Two of the most amazing spacecraft ever launched would never have taken flight if the stars hadn't aligned. In this instance, the four largest planets in our solar system were the stars. As a result of this coincidence, a spacecraft could gain speed from the gravitational pull of each large planet it passed, as if being pulled along by an invisible rope that suddenly broke, sending the probe flying on its course. One drawback, though, the alignment only took place once every 176 years. A spaceship would need to be launched by the mid-1970s to reach the planets while the lineup was still in effect. As it turned out, NASA created two spacecraft to make the most of that once-in-a-lifetime chance. Within 15 days of one another, Voyager 1 and Voyager 2, which were identical in every way, were launched in the summer of 1977. They have been operating in space for almost 45 years and send data back to Earth every day from the solar system's farthest known planets. They have lasted longer and traveled further than any other spacecraft in history. According to our best understanding of the dividing line between the Sun's sphere of influence and the rest of the galaxy, they have entered interstellar space. They are the first items created by humans to do so and will continue to hold this distinction for at least a few more decades. Overall, not a bad record given that the Voyager missions were initially only intended to last for years. The Voyager spacecraft's early observations of Jupiter's and Saturn's moons stunned researchers 40 years ago. They revealed the presence of active volcanoes and furred ice fields on worlds that astronomers had assumed would be as inactive and crater-pocked as our own moon. Voyager 2 was the first spacecraft to pass by Uranus in 1986, and 3 years later, it flew by Neptune. It is the only spacecraft to have traveled in this way so far. They are currently surprising physicists with a number of unexpected discoveries about that unexplored region as pioneering interstellar probes more than 12 billion miles from Earth. Finally, their amazing voyage is coming to an end. NASA has turned off heaters and other non-essential components during the past 3 years to stretch the spacecraft's energy reserves as far as possible, estimated until 2030. It is a bittersweet moment for the scientists on board the Voyagers, many of whom have been involved with the expedition from the beginning. They are now faced with the completion of a project that is far beyond their highest hopes. 546 days after its launch in March 1979, Voyager 1 arrived at Jupiter. Voyager 2, which had taken a different course, arrived in July of that same year. For its VidCon cameras, which used red, green, and blue filters to create the full-color images, both spacecraft were built to be stable platforms. Since their rotating velocity is more than 15 times slower than the crawl of a clock's hour hand, they barely spin at all as they travel across space, reducing the likelihood of visual blur. The spacecraft began transmitting the first images of Jupiter despite still being around 3 to 4 months away from the planet, to the delight of standing room-only crowds at JPL. It was absolutely unexpected when Io showed up in color. Prior to the Voyager missions, it was believed that all moons in the solar system would appear similar, drab and cratered. The incredible diversity of moonscapes the Voyagers found near Jupiter and Saturn was not predicted. The first indication that there might be more moon types than astronomers had imagined appeared when the Voyagers were still 1 million miles or so away from Jupiter. One of their devices, the Low-Energy Charged Particle (LECP) detection system, detected some peculiar signals. Io had active volcanoes, as revealed by the cameras on board the Voyagers. The little world, slightly bigger than Earth's moon, is now understood to be the solar system's most volcanically active body. The components ejected by the Moon's volcanoes give Io its hues and the anomalous ions that strike instruments. Pele, the greatest of Io's volcanoes, has produced plumes 30 times higher than Mount Everest, and its ash field is almost the size of France. The Voyager spacecraft captured more than 33,000 images of Jupiter and its satellites in total. Every photograph seemed to reveal something new. Jupiter had rings. Europa, one of Jupiter's 53 named moons, had an icy covering that was shattered and is now thought to be more than 60 miles thick. The spacecraft received a farewell kick of 35,700 miles per hour as they were leaving the Jupiter system, thanks to a gravity assist. Without it, they would not have been able to escape the Sun's gravitational pull and travel to another star. The Voyager split off at Saturn. Voyager 1 passed by Titan, the moon cloaked in orange smoke, and then turned north, away from the plane of the planets. After hurtling through Saturn's rings and taking hundreds of strikes from dust particles, Uranus and Neptune were the next stops for Voyager 2 alone. In 1986, Voyager 2 discovered 10 brand new moons orbiting Uranus, bringing the planet's ringed world count to an ever-growing number. 3 years later, Voyager 2 observed the fastest wind speeds ever recorded for a planet in the solar system, up to 1,000 miles per hour, as it passed around 2,980 miles above Neptune's azure methane atmosphere. Triton, the biggest moon of Neptune, was discovered to be one of the solar system's coldest locations, with a surface temperature of just 391 degrees Fahrenheit, 235 degrees Celsius. Nitrogen gas and powdered particles were ejected 5 miles into the moon's atmosphere by ice volcanoes. If Carl Sagan, an astronomer who was a member of the mission's imaging crew, hadn't been there, Voyager 2's pictures of Neptune and its moons would have been the last ones ever taken by either of the spacecraft. NASA intended to turn off the cameras on both spacecraft once the Grand Tour was formally over. There would have been no photo opportunities after Neptune, only the unending nothingness and impossibly far-off stars. Despite the project being extended in the hopes that the Voyagers would reach interstellar space and being renamed the Voyager Interstellar Mission, Sagan pleaded with NASA leaders to order Voyager 1 to send one more batch of pictures. As a result, the probe pointed its cameras back toward the inner solar system on Valentine's Day in 1990 and snapped 60 final pictures. Earth was captured in the most mesmerizing of them all, known by Sagan as the pale blue dot. At a distance of 3.8 billion miles, it is still the furthest depiction of our planet ever captured. Earth is hardly discernible in the photograph, hidden by dim sunlight that was reflected off the camera's optics. It doesn't even take up a whole pixel. Both Voyagers are now so far from Earth that a one-way radio signal traveling at the speed of light takes almost 22 hours to reach Voyager 1 and just over 18 hours to catch up with Voyager 2. They advance by 3 to 4 light seconds every day. The NASA Deep Space Network, a trio of tracking facilities dispersed across the globe that allows for continual communication with spacecraft while Earth revolves, is their only connection to Earth. The Voyager signals are getting fainter and fainter as they move farther away from us in space and time. The world is really noisy, everything produces noise, radios, televisions, cell phones, etc. Thus, hearing these slight squeaks from the spacecraft becomes increasingly difficult. Even though they are faint, those whispers have altered what astronomers anticipated the Voyagers would discover as they moved into the interstellar portion of their journey. You're advised to avoid confusing the solar system's limit with that of interstellar space. The Oort cloud, a far-off collection of comet-like entities held together by the gravity of the Sun, may extend halfway to the nearest star. It will take at least another 300 years for the Voyagers to arrive at its near edge. However, interstellar space is far more accessible where the solar wind phenomena end is where it starts. The solar wind is a continuous outpouring of charged particles and magnetic fields that the Sun, like all stars, emits. Moving at hypersonic speeds, the wind blows out from the Sun like an inflating balloon, forming what astronomers call the heliosphere. The magnetic field of the Sun is carried into space together with the solar wind. The heliosphere's expansion is eventually restrained by interstellar matter pressure, forming a boundary with interstellar space that is preceded by a massive shock front known as the termination shock. The heliopause is a border between our solar system and interstellar space, and estimates of its distance before the Voyager missions fluctuated significantly. According to Get, some of them were just assumptions. One early guesstimate located the heliopause as close as Jupiter. Garnett's calculations from 1993 put the distance at around 25 times further, between 116 and 177 astronomical units. $1 or 93 million miles is the distance between the Earth and the Sun. Garnett's projections from 1993 were accurate. Before one of the Voyagers ultimately reached the heliopause, about 20 years had elapsed. Voyager 1 had actually detected the anticipated rise in plasma density. Its plasma wave detector had inferred an 80-fold increase, but there had been no indication of a shift in the ambient magnetic field's direction. Shouldn't that change have been apparent if the vehicle had traveled from a place where the magnetic field originated from the Sun to one where it came from other stars? That was a shocker. In November 2018, Voyager 2 arrived at the interstellar seashore but did not notice any magnetic field changes. When the spacecraft reached the heliopause at $120 from Earth, the same distance reached by its twin 6 years earlier, it added still another riddle. All theoretical models predicted that the heliosphere should ebb and flow in time with the Sun's 11-year cycle, but this did not fit any of them. The solar wind ebbs and flows. At that time when Voyager 2 arrived, the solar wind was at its strongest, and if the predictions were accurate, the heliopause should have been further out than $120. Theorists' models of the interaction between the heliosphere and the interstellar environments are getting more intricate now that the Voyagers are providing them with some actual field data. According to the general image, our Sun left a hot ionized zone and entered a patchy partially ionized section of the galaxy. The hot zone probably developed as a result of a supernova, an ancient star nearby, or perhaps several exploded at the end of their lives, heating the surrounding area and removing electrons from adjacent atoms in the process. One way to conceptualize the boundary enclosing that area is kind of like the seaside, with all the water and the waves whirling and mixing together. Magnetic fields twist and turn because we are in that sort of tumultuous area. Although the degree of turbulence observed can vary depending on the method of observation, it is not like the smooth magnetic fields that theorists typically prefer to draw. As a result of the heliosphere's influence on the interstellar medium, the Voyager's data reveal numerous small-scale changes near the heliopause but negligible field variations at vast scales. It is anticipated that the spacecraft will eventually leave those turbulent zones behind and come into contact with a pure interstellar magnetic field. Saying goodbye to these innovative spacecraft won't be simple. Seeing things come to an end is difficult. There are currently 5 operational instruments aboard Voyager 2 and 4 on Voyager 1. They are all propelled by a mechanism that transforms heat from plutonium's radioactive disintegration into electricity, but NASA has been forced into triage mode as a result of the power output diminishing by roughly 4 watts annually. The Voyager's adventures will continue even when they are entirely silenced. Voyager 1 will pass Proxima Centauri, our closest neighboring star, in 16,700 years. Voyager 2 will follow 3,600 years later. After that, they will spend millions of years orbiting the galaxy long after our Sun has disintegrated and the heliosphere has vanished. Not to mention one pale blue dot, they will still be there, largely undamaged. They might be able to deliver a final message at some point throughout their journey, however, it won't be broadcast over the radio. If it is, it won't be by humans. 2 recordings, another form of antiquated technology, are used to convey the message, but not your typical plastic version. These are formed of copper, have a gold coating, and are enclosed in aluminum. Images and noises intended to provide a feeling of the world the Voyagers came from are encoded in the grooves of the Golden Records, as they are known. There are 90 minutes of music, including Bach's Brandenburg Concerto No. 2 and Chuck Berry's Johnny B. Good, as well as images of kids, dolphins, dancers, sunsets, and sounds of crickets, rain, and a mother kissing her child. Jimmy Carter, who was President of the United States at the time the Voyagers were launched, also left a message. We cast this message into the cosmos, it reads in part. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope, determination, and goodwill in a vast and awesome universe. Thanks for watching another episode of Space Discovery. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.